So supernovae are some of the most energetic events in the universe. They happen as a massive star explodes at the end of its life. We get some of the most beautiful astronomical pictures out of their remnants. So here, for example, that's the Crab Nebula, which formed after a supernova exploded in the first millennium, and it was recorded by Chinese and Japanese scholars. We expect them to happen 2 to 4 times per century in the Milky Way, with the last one happening about 40 years ago. So these are very rare events, and we want some type of warning for them to be able to, for example, redirect telescope time and be better prepared to get most of the scientific information you can get out of them. So apart from giving warning for supernovae, detecting them could provide a better understanding of massive stars, and this is because at the end of its life, the star will emit more and more of these very weakly interacting particles, which are called neutrinos, and we think that in the last days of the star's life, it could go over the threshold for detection at Earth, and these neutrinos can tell us about the evolution of the star towards the end of its life and its structure. It could also give us insights into the physics of neutrinos and particle physics in general. So in this presentation, I'll just go over how a massive star evolved at the end of its life. Then I'll tell you about how we can hope to detect them inside neutrino detectors at Earth, and specifically Super Kamiokande. And finally, I'll tell you how you build a pre-supernova alarm and how I went about trying to improve the current one at the Super Kamiokande. Cool. So for most of its life, a star burns hydrogen to helium in its core, and this provides most of the energy it needs to counteract the gravity, because it is very massive, any star. As the star evolves, helium will accumulate at its core, and where helium is, there's no fusion, so gravity wins over. The core contracts until the temperature reaches a threshold for helium to burn into carbon. Cool. So this continues on for massive stars for heavier and heavier elements. Heavier and heavier elements, so carbon to oxygen. Oxygen to silicon, and silicon to iron. You can't extract any more energy when you burn iron, and so fusion stops in the core, no more energy, and the star collapses on itself under its own gravity, and this is what eventually leads to a supernova explosion. So as the temperature increases, there's more and more neutrinos produced in the core as the temperature increases, and we think that from silicon burning onwards, so a few weeks before the supernova explodes, this could go over thresholds for detectors on Earth. And I studied a few neutrino models for my project, and they do all follow the same trends with a massive increase towards core collapse, which is at 0 here. And however, they do have a few differences between the models, such as these peaks, which are from silicon shell burning. And if we can detect these peaks from the neutrinos, we could potentially be able to know which model is the most likely. So the next natural question in my project was, how do we actually detect these neutrinos on Earth? And the way we do it in Super Kamiokande is with this. So we do it in Super Kamiokande. So Super Kamiokande is this huge 50 kiloton detector, which is in Japan, and So the tank is 50 kilotons of water surrounded by walls of these very shiny baubles, which are called photomultiplier tubes, or PMTs. And how it works is that neutrinos will interact with the medium, so the water, and from this interaction, light will be produced, and the light will be detected by one of these PMTs. So for this PMT, you get light which is emitted inside the detector, and it registers as a hit or an interaction. So just like a 2D model, very simple, you get the 50 kiloton of water, which is most of the detector, with the 10,000 PMTs which surround the water. And of interest to my project is that the detector was recently doped with an atom which is called gadolinium to 0.03%, and this increases the sensitivity to the interaction we're interested in, which is called inverse beta decay. So inverse beta decay is the main channel for interaction for these very low energy neutrinos from pre-supernova stars. And what happens in this interaction is that an electron antineutrino, which is a type of neutrino, interacts with a proton, and from this interaction forms a positron, which is an anti-electron. And if it travels faster than the speed of light in the medium, it will emit a type of light which is called Cherenkov radiation. And you also get a second particle, which is a neutron, and a neutron will be absorbed by the gadolinium, which is now in the detector. And the gadolinium will excite, and as it de-excites, it will emit a cascade of these of very energetic light gamma rays about 85 microseconds after the light from the positron. And from this combination of the two signals, you get a very characteristic distribution in inverse beta decay signals. So you can see it here for the distance between the two signals and the time you expect from the two signals. However, this is not quite enough to be able to differentiate it completely from the background for the sensitivities we want for the detection of these electron antineutrinos from pre-supernova stars. And what I did in my project is that I put it in a machine learning algorithm, and this is also what happens inside SuperChemiCandae with a couple of the variables. And you can differentiate the background, which is in orange, and the signal much more readily. And this is what is used for event pre-selection and event selection. So with the efficiency I get from this, I get the following significance of for the signal. And the main point of this plot is that when the significance goes over 3, this means you can put a warning. So if you get so many inverse beta decay signals that it goes over the 3 sigma threshold, that means you can potentially be in the situation that you're detecting some electron antineutrinos from pre-supernova stars. And I did manage to increase the sensitivity by a few hours compared to the one currently inside SuperChemiCandae, by a few hours. So, but you do get a very quite a difference in time between the 3 models here. So 15 hours for the blue model, 22 hours for the black model, and out of the hours for the orange model. So to conclude, so you do get, you can get hints about which model is the most likely which pre-supernova model is the most likely from the warning times. And this could tell us which stellar evolution model is the most likely and tell us about how stars evolve towards the end of their life. And although I did manage to optimize the current background rejection, there may have been bias introduced in my signals sample, and so further study is needed to know if this machine learning algorithm is viable or not. So, thank you.